So far we have only studied one kind of black hole, which is the Schwarzschild black hole, and that is because we haven't found any other black hole solution. It is clear that if we want to find more general properties of black holes, we need to study more examples, and for that we have to find more black hole solutions. We cannot do that if we stay with static spherically symmetric black holes in absence of matter, because the Birkhoff theorem tells us that the Schwarzschild black hole is the only one. And if we go away of staticity and spherical symmetry, things become really complicated, as we'll discuss when we review briefly the Kerr-Newman black hole. A simple solution is to couple gravity to some simple kind of matter. In this case would be the electromagnetic field, and we keep asking that the solution that we search for are static and spherically symmetric, because we know that static spherically symmetric metrics, independently of the matter that we have, depend only on two functions of the radius of the radial coordinate. So these are the setup will be simple enough to find the explicit solutions. So let's consider the Einstein-Maxwell theory, which is the theory that when one obtains when one couples gravity to the Maxwell field. And let's consider this action that has a slightly different normalization for the electromagnetic field, but this is one that simplifies calculations. Instead of having 1/4 of f squared, we just have minus f squared. Okay. You can always arrive to this normalization by rescaling the electromagnetic field, so there is no problem with this. Okay, the Einstein equations now take this form. I am setting G equal nothing is, I don't need to set anything to any value, because this is an overall factor. Okay, so since it is an overall factor in the Einstein equations, I will not get this typical factor of 8 pi G blah blah blah, so I only get 2 times, and now it is the energy momentum tensor of the electromagnetic field. So this is 1/4 of G mu nu f squared. And you also get the Maskwell equations. Okay, now with the metric. And remember that we can rewrite this up to a factor of 1 over the square root of G as this divergence. Okay. In practice, this is the thing that we will compute. If we decide to write the answers for the electromagnetic field, because as usual we will assume that there is some ansatz for the metric and now also for the electromagnetic field, we will plug it into these equations and we will try to solve it. If our ansatz is given in terms of the field strength F mu nu, then we would have also to solve the Bianchi identity. Okay, because then the Maxwell equations include this piece. The solution to this piece is always locally that F is given, F mu nu is given by 2 times the antisymmetrized partial derivative of A mu. So these two things imply each other locally. Okay. So now what is the answer that we are going to make? Staticity and spherical symmetry tell us that the metric will be given by this form, for instance, and this is the same that we used to find the Schwarzschild solution. So we have computed the curvature and everything. Okay, and how about the electromagnetic field? The electromagnetic field will have to be also static and spherically symmetric, and something of this kind is given by an electrostatic potential, which is a function of r only, phi r. For instance, the Coulomb field is precisely of this kind, at least in a certain gauge. Okay, obviously this ansatz is given in some gauge. Now we have to compute the Einstein tensor, but for this metric, but this is something that we already did. At least we computed the Ricci tensor in the case of the Schwarzschild solution. And so what we haven't computed yet is F mu nu and everything for this electromagnetic field given by this potential. Okay, we need to compute F mu nu because it appears here in the Maxwell equation and also appears in the energy momentum tensor. Well, the only component which will be different from zero will be the FTR component or the FRT. Maybe in this order is better. The difference is just one sign. But in this ansatz, this is the only thing that which will be different from zero. In this gauge, I mean, and this is just phi prime. This is the way we are going to write it. Okay, where the prime means a derivative with respect to r. This is the only thing on which this metric depends. Then we have to compute FRT with indices with upper indices, and there is no other component because the metric is diagonal. Okay, so if I raise one index r, I get another index r and nothing else, and the same with t. And this is GRR, GTT, FRT with indices down. One is the inverse of the other up to a sign. GTT is lambda, GRR is minus 1 over lambda, so this is minus FRT, so this is minus phi prime. Okay, the other thing that we need to compute is the square root of g, at least to check or to impose the Maskwell equation, and this is just lambda times 1 over lambda, this is 1, and then we have r squared times r squared sine square of theta, so this is r squared sine theta. Now let's go to the Maxwell equations. This is partial mu r squared sine theta. Okay, for the moment we just keep it. And there are only two possibilities, FTR or FRT. If this is the free index t, then this has to be r and this has to be r. So this is one of the questions that has to be checked. And the other possibility is that the free index, okay, the one which here is written as nu, is r. So this will be t, FTR. And I don't know why I wrote this, but clearly nothing depends on t, neither here nor here nor here, so this is 0. In the t equation, in the one in which the free index is t, this sine of theta can get out of the equation, and we just have r squared phi prime with another prime equal to 0, but we know how to solve this because this tells us that r squared phi prime is some constant, and then phi prime is of this form. We cannot integrate this equation until we know what r squared as a function of a small r is, but okay, the general form of phi prime is this, and this is enough to come back to this expression for FRT and then compute the complete energy momentum tensor, which is what we are going to do now. Since F squared appears in all the components of the energy momentum tensor, we start by computing it. This is F mu nu, and now the only component of F mu nu which is different from 0 is FTR or FRT. So if this mu, nu and r and t, this has to be r and t, And there is another term in which instead of RT you have TR and TR, but they differ from two minus signs from this term, so in the end you just get a factor of 2 here. Now FRT is with upper indices is minus FRT with lower indices, and FRT is phi prime, which we just found here to be a over r squared. So this is minus 2a squared divided by r4. Okay, and this is the first thing that we have to compute. And now the other terms that are well, that should be computed are these ones. Okay. Well, if this energy momentum tensor is going to be the one corresponding to this metric, since the Einstein tensor for this metric is diagonal, we expect the energy momentum tensor to be diagonal. So only terms such as ft nu should appear, and then r theta theta phi phi. Okay, this is not too difficult to see that this is the case. Only if these two are equal, then these two can be also equal, and since only the components TR are different from 0, then this is more or less guaranteed. Okay, in this case, if we are talking about the TT components, well, nu has to be r. Okay, this is the only possibility, and if we lower this index, we have the inverse of GRR. Okay, let me do it slowly. This should be FTR and FTR. That's because the metric is diagonal, and this is minus lambda. Minus lambda. So we get minus lambda FTR squared, and FTR squared is A squared over R to the fourth. Okay, now the R component is similar, but now you have GTT and FRT squared. GTT inverse is 1 over lambda, and FRT is A squared divided by R fourth. Well, the rest of the components with theta theta and phi phi give you 0, because there are no components with theta and phi. And now combining this with f squared, okay, we have ft nu minus half gtt f squared. Now we have computed this first term. This is minus lambda a squared r fourth minus, sorry, I wrote that half, but this is a fourth, minus 1 over 4. GTT is lambda, and f squared is minus 2a squared r fourth. Okay, here we have plus 1 half, here minus 1, so in the end it is minus a half lambda a squared r fourth. R nu f r nu minus 1/4 GRR f squared. F r nu, we computed it here. This is 1 over lambda a squared r fourth minus 1 over 4. GRR is minus 1 over lambda, and f squared again is minus 2a squared divided by r fourth. Here we have 3 minus signs, and again we get a minus 1/2, and exactly the same that you get in this in the first term. So this is 1/2 1 over lambda a squared divided by r fourth. Okay, theta theta. You have we know it's 0 f theta nu minus 1/4 g theta theta f squared, and this is minus 1/4 minus r squared and minus 2a squared over r fourth. So there are 3 minus signs. This is minus 1/2 a squared and only r squared. And the phi component should be equal to sine squared theta, the theta component. Well, this is easy to see because g theta is sine, sorry, g phi is sine squared theta g phi. So you are going to get exactly this, minus 1/2 sine squared theta a squared over r squared. And these are all the terms that we need to compute. In fact, we don't need to compute this one. Okay, we did it just as a check, because we know the Einstein tensor also obeys this relation. So if the theta component of the Einstein equations are satisfied, then the phi component will also be satisfied. And we only need to check 3 of them. Okay, let's start now with the Einstein equations, and we can do it just because we don't want to compute the Einstein tensor. We computed in the past the Ricci tensor. Let's just take the trace of the Einstein equations. Remember that in this case this is just f mu rho f nu rho minus 1/4 f g mu nu f squared. Now if you take the trace with g mu nu, you get g mu mu, which is r minus 1/2 times 4, which is the trace of the metric, times r. This is minus r, and here you have 0 because the energy momentum tensor of the electromagnetic field is traceless. Here you are going to get f squared, okay, a factor of 2 minus 1/4 and the trace of g mu nu f squared, okay, which is 0. So you find that r is equal to 0. You replace this result into g mu nu, and you find that r mu nu is equal to the energy momentum tensor. Okay, so now we go component by component. Okay, so we start with the TT component, and if you search in the I think it was the 5th lecture, we had the TT component of the metric that we are using, of the Ricci tensor, and this is nothing but minus lambda divided by 2 r squared lambda prime, and now we have 2 times and the TT component of the energy momentum tensor, which we just computed here. It is minus 1/2 lambda a squared divided by r fourth. Okay, let me simplify this a bit. Okay, the minus 1/2 and the factor of 2 just cancels, so this is just this. Okay, now we can simplify this further, but let me go to the R component, because we know that the R component involves the RTT component. This is something that maybe we remember from the lecture 5. Okay, here you can write R, the R component of the Ricci tensor in this way. Okay, and then you recognize that what is inside of this square brackets is RTT. And there is another term which is 2 times R double prime divided by R. And here we have 2 times the Newtonian tensor, the components that are of the Newtonian tensor, which is 1 over lambda A squared divided by R squared. Okay, since this is RTT, we can probably replace the result of this equation. Okay, we can replace all this, which has 2 derivatives, by this, which has no derivatives. But we will do it later. Let's first write the theta component. And this is a half of lambda R squared prime and another prime minus 1 equal to 2 times the theta component, which is minus a half. So A squared divided by R squared. These are the 3 equations that we have to solve. And obviously we just come and replace, as we said, RTT by its value, which is this. So we get minus lambda minus 2 times minus lambda A squared divided by 4th plus 2 times R double prime divided by R equal to 1 over lambda A squared divided by R squared. Sorry, this should be 4. Okay. Yeah, it is 4. I didn't copy it correctly. Okay. Now lambda minus 2 times lambda is 1 over lambda. So this term and this term cancel. And you get again the same equation that we obtained for Schwarzschild. So R is, capital R is AR plus B. And as usual, we eliminate this B by a shift of the coordinate R. That doesn't change our answers for the metric. It doesn't change the general form of the electromagnetic field either. And then on top of this, we choose A equal to 1. Well, there is another A, so maybe I should call it C. Okay, C equal to 1. So in the end, R is equal to R. This is the result. Now we go back with this result to the TT component. And this is minus lambda divided by 2 with small r squared. And we have r squared lambda prime prime equal to minus lambda A squared divided by small r to the 4th. Okay, these lambdas disappear. Now this is 1. And r squared disappears. And in fact, if we multiply everything by r squared, by r 4th, we get this r squared here, or we don't need to do this, maybe we leave it like this, and this factor of 2, maybe we take it to the other side. Now in this way, here you have a derivative of all these with respect to r, and here you have just a function of r that you can integrate. Okay, you integrate these two pieces. This gives you r squared lambda prime, and here you have minus 2a squared divided by r plus some integration constant. that by sheer lack of imagination I call B. Now lambda prime is equal to minus 2a squared divided by r cubed plus b divided by r squared. Again, this is the lambda, the r. Here you have a function of r, so we can integrate this. We integrate both sides, and this gives lambda on this side, and here the integral of b divided by r is minus b by r squared is minus b divided by r. This is plus a squared divided by r squared, and then we have another integration constant. See, this determines completely lambda. Okay, here b and c are integration constants to be determined, by a is different. Okay, it is it is also to be determined, but it is exactly the same a that appears here. Okay, now you can plug this lambda into the theta theta component of the Einstein equations, and you get a square bracket c plus c minus b divided by r plus a squared divided by r squared. This multiplied by r2 squared, which is 2 times antiderivative, so this is just 2 times r, and another prime, and this should be equal to minus a squared divided by r squared. Okay, sorry, and there is this minus 1. Yeah, okay, so let's compute this. This factor of 2 cancels this one. You have the derivative of CR gives you C. Then you have the derivative of minus b, which is 0, and then the derivative of a squared over r, that gives you minus a squared divided by r squared. Minus 1 equal to minus a squared divided by r squared, which means that this integration constant has to be 1. Okay, then there is only one free integration constant, this b, plus the original one that depends on the electromagnetic field, which is a. And the result, if we collect everything, is this one. And a t, this is, well, remember, we have that phi prime is a divided by r squared, and this was a t was phi, so if phi prime is a divided by r squared, then phi is equal to minus a over r, and then at is minus a divided by r, and this determines completely our solution, a solution that has radial, okay, because we have imposed spherical symmetry, a radial electric field that decays like 1 over r, clearly is a Coulomb field, and this constant a should be related to the electric charge. We will see later about the normalization, etc. This constant b, okay, according to our experience with the Schwarzschild black hole, should be related to the mass. Also because this 1 over r term will be associated to the Newtonian potential. So we know that this b with this minus sign here should be 2 times the Newton constant times m. Okay, let me write the full solution. This is known as the Reissner-Nordström solution. Well, we are working in units of, well, let's leave this G here, doesn't really matter. And plus A squared divided by R squared minus this same function here divided minus R squared the omega squared, okay, because we also found that R is equal to R, and AT is minus A over R. These are the physical fields of the solution. Okay, so a part of the determination of the mass, which we know that it is 2gm, because if you expand this metric asymptotically, well, first of all, you find that the metric is Minkowski with the standard normalization. This is what we achieved by setting the integration constant here equal to 1. All these terms decay with 1 over r or 1 over r squared, so you find Minkowski in spherical coordinates. This means that this solution is asymptotically flat, is asymptotically Minkowski. The next term in the expansion gives you the Newtonian potential, so it is 2gm, and this relates the integration constant m to the mass. Also, this term, okay, in the electric field, this is electrostatic potential, it must be related to the charge and appears here squared. This solution, which we are going to study now, is the Reissner-Nordström solution. And we will see that it describes a black hole in certain conditions that has mass and a charge. It is still static, spherically symmetric. Okay, I think in the lecture notes, the next thing that we do is to study A and show that indeed is related to the electric charge. In order to prove this, we are going to first write an alternative expression for the electric charge. Typically, the charge, which is enclosed in some volume, could be given by the integral over this three-dimensional volume of the zeroth component of the charge and current density. This current density is the thing that appears in the right-hand side of the Maxwell equations. So this is what you would compute. Now we want to express this in a more covariant form. Okay, the way to do it would be to use this definition for the surface element. This is equivalent to this, okay, and this is just more covariant. The fact that this three-dimensional surface is a space-like surface, then this implies that the normal vector to a space-like surface is time-like. And if it is time-like, it will pick the zeroth component or another combination of components, which in any case will be time-like and will correspond to the charge as seen by somebody associated to that vector. Okay, this is really the good expression. This is the one that first comes to your mind, but this is a more precise and covariant expression. Now, using the equation that I just deleted, we can replace the current by the divergence of the Maxwell field. And using an identity that basically is another version of the Gauss Theorem, you can re-express this integral as another integral over the boundary of this volume. Okay. Sorry, the factor, I don't know why I wrote this factor of 1/2 here. The factor of 1/2 should come here when I write this. And this is an element of surface. Okay, this is a hypersurface, three-dimensional. In a space of 4 dimensions, it is characterized by the direction which is normal to the hypersurface. Now, a surface, two-dimensional surface in 4 dimensions is characterized by 2 vectors normal to this surface. Okay, this is why you have this mu and nu here. This is, if you want an intuitive explanation of what this mu and nu mean. Okay, the important thing, if we want, we can express this using the definition of this form of this, this integration element. You can write it like this: a half and another half, okay, and this divided by square root of g, and also dx nu. This would be the complete form. Now, this defines, okay, the component of what are called the Hodge dual of f mu nu. This you don't need to know, okay? I didn't explain this, but I think you should hear once about it. These are the components of the Hodge dual, and together with this factor of 1/2 and dx nu, this is expressed as this integral. Okay, this is an integral of a 2 form over this 2-dimensional space, which is the boundary of the 3-dimensional volume. When you express this thing in more pedestrian terms, in the end, what you are doing is integrating, for instance, over the 2-dimensional sphere that is the boundary of a 3-dimensional ball, okay, in a 3-dimensional space. This 3-dimensional spherical volume, it has a boundary which is a 2-dimensional sphere, and this is basically the Gauss Theorem, expressed in maybe a strange language that probably you haven't seen yet, but it is exactly the same. So, although I'm not going to do this calculation in detail, what you need to know is that when you do the calculation, you find for the field that I have that we have here, okay, you just go through this computation, and you find that the volume enclosed into a surface, which can have any radius. Okay? Typically, you take the radius at infinity, so you enclose all the charge, but this is not really necessary. Anything that includes r equals 0 will give you the same result. The result way is that this is minus 4 pi a. Okay, so this is the relation between the integration constant a and the charge of the space-time. Now this is the charge of the whole space-time. Okay, because now I'm not using any volume that includes the origin has this. Typically you normalize the charge with this factor of 4 pi, so it doesn't appear there because it is quite ugly. So in the definition you probably want to include this rationalized this factor to rationalize units, so you don't get these factors of 4 pi. This is just not essential for us, okay? And we can choose whatever units. And also we could discuss a long time about the design of the charge that has to do with the orientation of the space-time. I don't know, okay? This is just to tell you that the intuition that this integration constant A is related to the charge is indeed true, is correct. And typically what you do, okay, is just choose some units in which this is Q or capital Q, depending on your preference. The only thing that matters is that with the conventions that we have chosen in the action, this integration constant is the same integration constant that appears there. Okay, so this is a space-time which is asymptotically flat, and it has a total mass m, and total charge q. It's spherically symmetric, and so on. And if we now we have to study the singularities that this metric can have, and it is very useful to find the places where the function lambda, remember that this is GTT, vanishes. Okay, since the function lambda can be written as with a common denominator r squared and then a second order polynomial, second degree, r squared minus 2m, I'm setting t equal to 1, plus q squared. You just have to find the roots of this polynomial. They are called r plus and r minus. And well, r plus and r minus are given by m plus minus the square root of m squared minus q squared. Okay, this is a very standard expression, and we would like to know what is the meaning of this r plus and r minus, which only exist as real values of the radius. Okay, I call it all the time radius. You know that is the radial coordinate, but it doesn't have much to do with the radius of a circle or a sphere. Okay, this is only real if q is smaller or equal than m. So there are, in this, this is really, people talk about families of solutions, which are given by, these are different solutions for each possible choice of the parameters m and q. These family of solutions include solutions which have, for which there are no real roots. There are solutions for which there is a single root, which is double when q is equal to m, and then there are solutions for which r plus and r minus are real, and there are two real roots. These three different cases will correspond to solutions which are very different physically. Let us try to find the singularities of the metric, if it has any. Looking at this form of the metric, you see that this term, so GRR, will blow up when this term in parentheses vanishes, which is when GTT vanishes, which is when r is equal to r plus or r minus. So r equal to r plus or r minus are two possible places where the metric is singular, and clearly at r equals 0 this term blows up and this term vanishes. Also this vanishes. We are used to this kind of singularity, but it is a singularity that in general relativity you have to really consider more carefully. Okay. So these are the three possible places where there is a singularity. I have ordered them in decreasing order, because by definition r plus is larger than r minus, assuming that they are different, they are real. Now you can check that r equals 0 is a curvature singularity. But that r plus and r minus are not. Just compute the Kretschmann invariant, for instance. It will give you blow up at r equals 0, just as it happened in the Schwarzschild case. So what are r plus and r minus? Chances are that these are coordinate singularities. In order to prove that, we will have to use some Eddington-Finkelstein-like coordinates that extend beyond the horizon. But before we do this, let's consider what are the possible horizons of this metric. Since the metric is static, then we know that the horizon coincides with a Killing horizon. We don't expect the Killing vectors associated to rotations to have Killing horizons. They don't. Okay, this you can see. So the one that should become important in this respect is the time-like Killing horizon, okay, which is nothing but partial t, and I don't need to compute it because we have constructed the general answers for this metric using the assumption that this is the Killing vector. The metric is independent of time, and then almost by construction this time-like Killing vector has to be just the partial derivative with respect to t. If I compute now k squared, this gives me gtt, which is 1 minus 2m divided by r. Well, maybe I write it in this factorized form, divided by r squared. Okay, so where is this 0? Okay, this is these are the places where k becomes a null vector. After it crosses r plus, assuming that r plus is real, then k will become space-like, then it will become null again at r minus, where there is another 0, and then it will become time-like again. These points are singular, but most likely, as in the Schwarzschild case, when we reconstruct the metric in better coordinates, well, these properties will remain there. So let's study them just like this. If r plus and r minus are real, then we expect that r plus will be the location of the event horizon. And it is the event horizon because r minus is always smaller than r plus. Okay. So what happens in the case in which m is equal to q? So this happens when m is larger than q. There is an event horizon there. R equal to r minus is something else. It is what we call a Cauchy horizon that you don't need to know now, but it is really not an event horizon. When m is equal to q, okay, what happens is that r is equal to r plus and is equal to r minus. Again, this is an event horizon. But there is a difference with this case. In this case, this is a bifurcate horizon, and in this case, this is a degenerate horizon. Bifurcate tells you that this horizon will have 2 branches and a bifurcation surface. Degenerate means that there is only 1 branch. And when r plus, so when m is smaller than q, there are no horizons. No horizons, but r equals 0 is still a curvature singularity, so there will be a naked singularity. Okay, so we developed this notion of Killing horizon because it allows us to find out where the event horizon is before we go to Eddington-Finkelstein coordinates or to Kruskal coordinates and reconstruct the whole space-time, and we find what is the causal structure of the space-time. And now this effort of studying the Killing horizon pays off because we have found all these possibilities and we know where the event horizon is. Now the analog of the Kruskal coordinates for the Reissner-Nordström space-time can be found, for instance, in the Hawking and Ellis book, The Large Structure of Space-Time, which is published in Cambridge University Press, and which is an excellent book, but it is more a book for people who already know many things. So it shouldn't be your first encounter with general relativity, but it contains a huge deal of information. In particular, it contains the change of coordinates from these Schwarzschild-like coordinates that we have been using so far to the Kruskal coordinates in the Reissner-Nordström case. The result that them can be conformally transformed to find the Penrose diagram, and let me just tell you what the result is. Okay, so in this case is sometimes called sub-extremal because this is called the extremal case. Okay, and this is the sub-extremal, because looking at the charge, it doesn't have enough charge to be extremal. Okay, so in this case, the Penrose diagram has this structure that I hope to draw in a decent way. Okay. Okay. Now, the asymptotic region, which is described by this original Schwarzschild-like coordinates, is just this one, this small square. Okay. This is square plus, square minus, I0, I minus, and I plus. Okay, and R equal to R plus corresponds to this whole line. Okay, and this one as well. More or less as in the Schwarzschild case, but remember in the Schwarzschild case there was a singularity here and a singularity here. Now this is not the case. The singularity is here and here. There are two copies, okay? And well, this is now R minus. And this is also R minus. And in fact, okay, although it is a Cauchy horizon, it has more or less the same structure as the event horizon, in the sense that it is also a bifurcate horizon. So this whole line is R minus, this whole line is R minus. There is an extra region that you didn't expect here, okay, and which is the region where you could try to find, to touch the singularity, or in the case the singularity will affect you. This is very similar to the region of Schwarzschild with negative mass. But okay, you could say, tell me what happens if I cross in this direction. There is more, of course. And what you find, in fact, okay, is another copy of this initial region here. Okay, where there are two asymptotic regions. Okay, there is R plus, and then again this reproduces itself also in this direction. Okay, so there is an infinite number of asymptotic regions, and you can, in this case, as different from Schwarzschild, in which there were only 1 and 2, so this was region 1, in Schwarzschild this was region 3, and we knew that you couldn't go from one to the other unless you travel faster than the speed of light. In this case, following a time like geodesic, you can follow this path and come out here. Okay, so this is sometimes called the Reissner-Nordström wormhole, in the sense that it is something that connects two asymptotically flat regions, in fact, two complete universes. Of course, you could also try to hit this singularity, but as we are going to see, this singularity is repulsive, just as in the negative mass Schwarzschild case. So you cannot touch it. It can affect you nevertheless. Okay, just again as in the negative mass Schwarzschild case. And well, this is the first time that you probably see a structure with universes that can be connected. But people do not trust this kind of solutions beyond this Cauchy horizon, R minus, because there is a singularity associated to this Cauchy horizon that we don't have time to study it. And it is expected that any perturbation will make this structure inside collapse. And people expect that it will be replaced by a Schwarzschild-like singularity, which is a space-like singularity instead of a time-like one. And if this is the case, then it doesn't make sense to consider the extension to these other universes. The same will be true for the Kerr-Newman black hole. It has a structure, the global structure, the maximal analytical extension also has many universes, but really the properties inside of the Cauchy horizon are really crazy. It will be a space in which you can always connect two events, no matter if they are in your future or past, because there is no future nor past. So it can be used to do to construct time machines, and so people expect that all those pathological properties will disappear the moment this singularity forms. This is part of the content of this strong cosmic censorship conjecture. We cannot study it, but you should at least hear once about it. How about, now this is the extremal case. Okay, remember that in the extremal case, the horizon is not a bifurcate horizon. And here the structure, the causal structure that one finds is this one, but now this is the whole space-time, our asymptotically flat region. Okay, I will not draw the I minus and I plus. This is R plus. Okay, and this is R plus because it coincides with R minus. What happens when you cross R plus is that you find the time-like singularity, which is over here. Okay, and there is another R plus here, and R plus also extends in this direction. And now there is another copy, another space-time with its own scribe minus and scribe plus. Okay, and the singularity, these are two different things. Okay, the singularity really runs along all this line, and there is an infinite number of asymptotic regions as well. Again, if you enter here, you can come out in another space-time, in another universe, another asymptotically flat region. And the singularity is time-like, and these pieces really behave in most respects as the negative mass Schwarzschild solution, with the difference that in that case these lines correspond to scribe plus and scribe minus, so you can never reach them in a finite time. And here they are, horizons, you can cross them in one direction. But the behavior close to this singularity is similar. The singularity is repulsive. There is a useful way to study this metric, rewriting it in a different form. So we are going to describe it as a kind of Schwarzschild-like metric, but with m replaced by a mass function. We know what this mr is in the Reissner-Nordström case. Okay, now the same inverted, the r squared minus r squared the omega squared. This is the Reissner-Nordström. If m of r is just m minus q squared divided by 2. I think I am using a small case. Q and 2R, sorry. Okay, so this is for Reissner-Nordström, but let's treat it like this and see, because then there is an analogy between this combination of mass and charge and the mass of the energy of the space-time. But this analogy will be made more formal or more visible if we write the Einstein equations and we identify the energy momentum tensor. Of course, this energy momentum tensor will be the energy momentum tensor of the Reissner-Nordström black hole when we replace m of r by this expression. But let's do it in general. Okay, we have the components of the Ricci tensor for a metric like this. So it is very easy to compute. This is done in the lecture notes. I'm not going to do it. And just identifying the Einstein tensor with the energy momentum tensor, you find the components of the energy momentum tensor are, okay, pi 2 lambda m prime, this is the derivative with respect to r, divided by r squared. TRR is 1 over 8 pi, again this is in units of g, capital G equal to 1, minus 2 lambda minus 1 m prime divided by r squared. T theta is 1 over 8 pi, 2 times m second derivative r, and T phi as usual is sine squared theta T theta. Okay, now we don't know what kind of matter distribution has produced this energy momentum tensor. Of course, for the Reissner-Nordström case, we know that an electric field will give rise to this energy momentum tensor, but we just want to compute these components of the energy momentum tensor in terms of this mass function, because then we can compute the energy contained in a certain 3 ball. How can we do this? I have insisted many times that there is no well-defined local energy density for the gravitational field. If there is no such a thing, then I cannot do the same for matter, because there is usually an interchange of energy between matter and the gravitational field. But when you have a space-time which is static, like this one, the fact that the space-time is static means that there is an equilibrium between matter and energy and gravity, okay? And there is no interchange of energy between both of them anymore. So you expect that the matter energy density is conserved, and that the gravitational energy density is conserved separately. Okay, this is something that you could argue in this way. In fact, if you construct this quantity, okay, where this k is the Killing vector, the time-like Killing vector, time-like Killing vector, then if you want to study if this current that we just defined, okay, is conserved, then you find that, this is on the one hand this, which is 0, on shell, plus T mu nu, and let me raise the index, then we have mu and nu. This is symmetric, so this is symmetric, and if this is a Killing vector, this is also 0. So this will be conserved. So in this particular case, we can study locally the energy density. And the energy then will be given by an integral over some 3-dimensional ball whose boundary will be a 2 sphere, if you want, okay, of this current that I just wrote. And in these coordinates that we are using, since k is just a partial derivative with respect to t, it only has t component, So this is the only thing that we need to integrate. Okay, this is a very easy computation, okay, which is done in the lecture notes, so I am not going to do it. And the result is that if this ball is well, constant time, but it doesn't matter because this space-time is time independent, and the ball is defined to be with a radius r, then it turns out that the energy contained in this ball is equal to this mass function, okay, computed for the same radius as this three-dimensional ball, which is more or less what you should expect. Okay, so what it means now, since m is m of r is m minus q squared divided by 2r, what you see is that when r goes to 0, this is the term that dominates and which is negative. So when you approach the singularity at r equals 0, e becomes negative. In fact, it goes to minus infinity. Goes to minus infinity when r goes to 0. So you find a singularity of the same kind as a negative Schwarzschild mass solution. Okay. This whole thing will act as something negative. We have written the metric in a Schwarzschild-like form, and you expect really the same result. Repulsivity, which is caused by a locally negative mass or energy density. This is somehow explains the behavior of the solution near the singularity. Now, although we have argued that there is a horizon that coincides with the Killing horizon and so on, it would be good to check all the things that we have said about the repulsivity of the singularity, and also the fact that r equal to r plus is a regular event horizon, by constructing Eddington-Finkelstein coordinates. And remember that these coordinates are defined, okay, well, in terms of this tortoise coordinate r star, whose fundamental property is that the r star is equal to the r over lambda when the metric is the way, has the form of r ansatz. Okay, because then this means that we could write the metric in the form lambda dt squared minus the r star squared minus r squared d omega squared, if we had decided to use this r star. But we are going to use this advanced Eddington-Finkelstein time coordinate. Okay, so in terms of this, you know that the metric will take the standard form lambda dv squared minus 2 dr dv minus r squared d omega squared. But now lambda, instead of the lambda of the Schwarzschild solution, will be this r minus r plus r minus divided by r squared. And well, once we are in this, we write it in this form, it doesn't matter if lambda vanishes at r plus and r minus, because the metric will be completely regular if it only has this part, okay, because of this is of diagonal, just as in the Schwarzschild case, as we explained. Okay, in the lecture notes you will find what is the explicit form of r star. I just copy it. It's given by minus m squared plus r0 squared. This r0 is m squared minus q squared. This is the arc tangent the hyperbolic arctangent of r minus m divided by r0, and everything divided by r0 plus m log r squared lambda plus a constant that you will adjust. Okay, what we are really interested in finding now are the geodesics, the radial null geodesics in this space-time using these coordinates, these Eddington-Finkelstein coordinates v, r, and theta and phi. Okay, as usual, we set theta to a constant and phi to a constant. This is the meaning of radial, and we need the components of the Christoffel symbols in the directions v and r. This is something that we computed in the Schwarzschild case in terms of lambda. So I just copy it. This is lambda prime. VVR is half lambda prime, and gamma VRR is minus a half lambda prime. But of course now lambda is a different function, is this one. Because the general form of the metric is the same and the components of the Christoffel symbols are the same, the equations that govern the time-like geodesics in this space-time are the same as those that govern geodesics in the negative mass Schwarzschild metric that we studied at the beginning of this lecture. And in the end, we find, if you remember, we found this equation from the Maxwell condition as the equation that basically tells us what are the possible geodesics. Yeah, so this is analogous to this one particle moving in this effective potential with this total energy. And if we draw this potential, which is lambda here, we know that it diverges, it has two zeros, and then it goes to one at infinity, asymptotically. Okay, these two zeros are minus, by definition the smallest, and are plus. So these are the two horizons, the Cauchy horizon and the event horizon. Now you have a particle of total mass epsilon squared, and it has, no matter how much energy it has, clearly can never reach the singularity at r equals 0, just as in the negative mass Schwarzschild space-time. However, there is a difference here. If the particle comes here, recoils at this point, well, it cannot go back beyond this point because this is a horizon. We know that, okay, maybe we shouldn't trust the interior of the solution, but we are studying the solution the way it is right now. If we knew how to replace the interior by something else, we would do it. But so let's stay with this for the moment. And what happens is that, on the one hand, the dynamics tells you that it has to go back. On the other hand, you know that this is a horizon, so it cannot go back past this point or this point either. Which means, or the solution to this conundrum or this apparent paradox is that when it crosses again this r minus, it is not the same r minus that it crossed at the beginning. It is another root of this equation, and remember that, okay, we have found that the Penrose diagram has this form, and that this is r minus. Okay, so this would be the singularity. This would be r minus as well. So the particle comes from this direction, it crosses r plus, it crosses r minus, and then it recoils near the singularity, but instead of going back to the same r minus, that this would mean that you are going back in time, it goes to across this copy of r minus, and then another copy of r plus, okay, now in this direction, and until it goes out at a different asymptotic region. Observe that by construction the particle cannot have this kind of epsilon square value because epsilon square is positive. On the other hand, it could have a bound motion from here to here, okay? But this kind of bound motion is analogous to this one, which is the one that we described before, which is unbounded in the sense that the particle comes from infinity and goes back to infinity. In that case, it's a motion that goes along this line, but it never, so it crosses r plus, r minus again, r plus, but it never goes all the way to infinity. Okay, this also, well, this tells you that by studying this simple equation, and if you know where the horizons are, you can infer what is the global structure of the spacetime in terms of new asymptotic regions and so on. It tells you, this tells you basically the fact that you you recoil and go back to r minus. This tells you that in r minus something happens, that there must be another copy of r minus that can be crossed when you move forward in time. So this helps you in constructing this, although this is just if you want a more or less heuristic argument, okay, and it has to be made more precise by constructing really all these other regions. We are going to end this video by studying these solutions of the Einstein-Maxwell system, and the motivation to find these solutions is the following. Let us consider the extremal Reissner-Nordström black hole. Remember that this is the solution that has m equal to q, so r plus is equal to r minus, if you want r0, which is square root of m squared minus q squared, is 0, and because it has two roots, this lambda can be written in this way, okay, because now this is equal to m, r plus and r minus is equal to m, and this is this squared and this squared, which is 1 minus m divided by r squared. Sometimes people write, they prefer to write the charge in terms instead of the mass, so they would write this, and of course it is exactly the same. So if you go to the metric, you find that it has this form. Okay, the same thing to the minus 2 minus r squared d omega squared. Now we want to rewrite this metric in isotropic coordinates. Isotropic coordinates are coordinates in which there is an overall factor multiplying dx squared. Okay, and initially, since we are using spherical coordinates, this dx squared will be some d rho squared plus rho squared d omega squared. Okay, we have studied how to do this. We go from the coordinate r to the coordinate rho, which means that we are going to get this factor here, and then d rho squared. We divide this by rho squared, and we have rho squared. And well, this will have the form of some overall factor multiplying this if this piece here is equal to this. Okay, then we take that term, which is equal as an overall factor. Sorry, you have to include, sorry, all this must be equal to this. Okay, and then there is a common factor, which is everything here, or r squared divided by rho squared, whatever it is. Okay, the differential equation is 1 minus m divided by r. We can take the square root already, and this is divided by minus 1, the r, the rho, and this has to be equal to r divided by rho. We separate variables, so r comes here, and the rho comes here, and we are going to integrate this. In this side we get the log of rho plus some constant, and here okay, let's see, this is r divided by r, but this has a minus 1, so this r and this r cancel, and this is just the integral of dr divided by r minus m, which is also another log. Okay, so it is log r minus m. Okay, so exponentiating, you get that r minus m is equal to some constant times rho. If you want, now you can choose this, but it will be a different constant. I am doing this all the time, okay, but you know that I can always redefine my constant so it appears multiplying rho. Okay, this is the relation between these two coordinates, and of course if I want, if my metric goes like r squared originally when r goes to infinity, and this means proper normalization of the Minkowski space-time in spherical coordinates, and I want the same for the metric in rho coordinates. This means that this c has to be 1. Okay, so I replace everywhere r by rho plus m, and so I have 1 minus m divided by r is this, which is rho divided by rho plus m, and this is 1 divided by 1 plus m divided by rho. Okay, the metric then is ds squared 1 plus m divided by rho. Now instead of square it will be to the power minus 2 dt squared, and okay, now I have this function that I have to multiply r squared divided by rho squared, which is the here it will be the common factor. R squared divided by rho squared is rho plus m divided by rho squared. So again, it's the same function, 1 divided by 1 plus m divided by rho squared. So here I have minus 1 plus m divided by rho squared, the rho squared minus, sorry, plus, because I have the common factor, rho squared, the omega squared. Okay, and I know that I can rewrite this as the x squared for some Cartesian coordinates related to the radial coordinate rho and theta and phi in the standard way. So this is the rewriting of the solution of the metric in particular, and well, you also have to rewrite the electrostatic field. In this case, remember that this was minus q divided by r, so will be, this is minus the sign of the charge. Okay, this will be kept here. Now I replace the charge by m, which is by convention positive, and this is rho plus m. Okay, this can be written in this way, because I want to use this function that appears everywhere, 1 plus m divided by rho. Clearly here I have something which is not quite the same. Maybe I can take this out, then I have 1 plus m divided by rho. So this comes like this, And this function, if I decide to call it h, so now I define 1 plus m divided by rho as h. Now I have h, and here h minus 1. Okay, and so in the end I re-express at as minus sign of the charge 1 minus h minus 1, or sine qh minus 1 minus 1. Okay, everything can be expressed in terms of h. ds squared is h minus 2 d2 squared minus h squared dx squared. And h is 1 plus m divided by x. Okay. Before I go on to find these Papa-Petro-Majumdar solutions, let me study this extremal Reissner-Nordström solution a bit more in these coordinates. Where is the horizon in these coordinates? Well, it was at r equal r plus, okay, which is m. The two horizons are minus and r plus coincide at the same point m, and this means that the horizon now is at rho equals 0. Well, this is one of these examples that show you that the so-called radial coordinate is not what you expect. Okay, so rho equals 0 is certainly not the origin of symmetry of a standard sphere or anything like that. In fact, rho equal to 0 is a sphere of radius m in these coordinates. What you can easily see is that the area of this surface, which is the horizon, is 4 pi m squared, because remember that the physical meaning of this radial coordinate r that we chose at the beginning was that precisely a spherical surface of radius r, or with constant value r and constant time, has a surface of 4 pi times this r squared. Here you don't see this so easily, okay? Okay, it is radial in the sense that it is invariant under rotations, but it is not a radius in any conventional sense. Okay, still the horizon has this area 4 pi m squared. Now there is something nice about this metric, which is the following. You can take what is usually called, and what I am going to do is not too rigorous, it is a bit heuristic, but it can be justified as something called a Penrose limit. Okay? I am going to do it in the standard pedestrian way that we do it, and which works. What I am going to take, as I was saying, is what is called a near horizon limit. So I am going to approximate the metric when r goes close to 0. Okay, I know that at r exactly equal to 0, h blows up. So this is not what I am going to do. What I am going to do is that the near horizon limit, sometimes people write nh for the near horizon limit, and we know that in this limit h goes like m over rho, because 1 is much smaller than m divided by rho when rho goes to 0. So I just approximate h as m divided by rho, and then you see that the metric, okay, takes this approximate value, rho divided by m squared minus m squared divided by rho squared, and this multiplies the rho squared plus rho squared the omega squared. Actually, what I should have taken the limit of the d theta theta and d phi phi terms separately, because there is this overall factor multiplying rho squared. So in fact what I have is h squared times rho squared. And in this case, when rho goes to 0, what I see is that this goes like m squared, okay, because the factors of rho cancel. You see this already here, but it would be more correct to do it in the other way. So I multiply and I simplify. Okay, let me see if I can do it. Okay. So this then multiplies this one, the rho squared, and minus m squared rho squared. The metric has decoupled in two pieces. This piece depends on t and rho, and this metric is independent on t and rho. It depends only on theta and phi. And this is actually the metric of a two-sphere of radius m. And you can see, okay, so this is S2 with radius m. And you can see that this is anti-de Sitter space-time with radius. So it's anti-de Sitter 2 with radius m. Remember what we defined as the radius of anti-de Sitter when we constructed anti-de Sitter as a hyperboloid. Okay, in fact, this metric is the metric of a space which is the direct product of these two. Well, here they look like subspaces. Of course, for each point, at each point of anti-de Sitter 2, there is a two-sphere, and vice versa. Okay, so this space is anti-de Sitter 2 times S2, both with the same radius. This is a new solution, in fact, okay, although we have obtained this in a not so rigorous form, and it doesn't have to be a solution at all. It turns out that this is a solution. It is the Bertotti-Robinson solution. And okay, you see that if we had the metric, if this function h was just m over rho instead of 1 plus m over rho, we would have obtained this metric instead of the extremal Reissner-Nordström metric. And this suggests that maybe there are more solutions for different choices of m, and that one has to find what is the general condition that h has to satisfy. For instance, it is clear that with or without an additional constant, m divided by x, which, by the way, is a harmonic function in three-dimensional space because it satisfies the di equal to 0, then it gives you a solution of these Einstein-Maxwell equations. So what we are going to do next is to well, take this solution, or this form of metric and electromagnetic field, some constant alpha that can be interpreted as the sign of the charge, h minus 1 minus 1. But now I don't specify h. I don't say what it is, and I consider this a general ansatz. I only say that h is some function of these coordinates, independent of time. That's all. We plug this into the Einstein-Maxwell equations, and we see what are the conditions that h has to satisfy in order to see for this to be a solution. At worst, we will recover the extremal Reissner-Nordström solution and the Robinson-Bernoulli solution only. Maybe would you find that h has to be m divided by rho plus a constant, or without a constant. Okay, but as we are going to see, there are many more solutions that one can find. So we have to proceed as we have done already many times. Now this is not a static spherically symmetric metric. It is static, but spherical symmetry will only take place if this h only depends on the absolute value of the vector x, but they can have more general dependency. So we cannot assume that. However, in this case, it is very easy to compute the Christoffel symbols in spite of the fact that there is no spherical symmetry, because you only have two kinds of terms to consider, terms with component t or component I. Okay, remember that here dtt is h minus 2 and gij is minus delta ij h squared. Okay, so it would start with this, and because there is no derivative, there is no dependence on time, you are going to find that gtt is 0, because this always involves derivatives of time only, and so on. I'm not going to do it. I suggest that you do it. The result for the Ricci tensor is given in the lecture notes. It is really easy and you can do it as an exercise. Although I know that these lectures are a bit long, so if you don't want to do it, just don't do it, okay? We also need to compute the field strength of the Maxwell field. Okay, clearly there are only two kinds of components that can be different from 0, it and ij. But since aj or ai are 0, the vector field is 0, then only this one will be different from 0. And this is di at minus at dt ai, dt is 0, so it's only di of at. At, the ansatz is that it is this constant alpha, which will be plus 1 or minus 1, can be associated to the sign of the charge. Okay, but we can keep it there, and then the derivative of h minus 1 gives h minus 2 dih. Okay, not too complicated. Well, with this you start computing the energy momentum tensor and so on, and the only thing that I'm going to compute is the Maskwell equation. So the Maskwell equation, remember that can be written in a simplified form like this. Okay, and the component nu, which is the free component, it can be either t or I. So what happens when we have t? Then mu has to be I. This is the only possibility. And well, it takes the form di, the square root of the determinant. Now the square root of the determinant of the metric will be as follows. Well, the determinant is h minus 2 times h squared cube. So this is h to the fourth with a minus, and then the square root will give you just h squared, so it's just h squared. And now when you raise the index I, you get a factor of h minus 2. When you raise the index t, you get a factor of h2, so they cancel, and up to a sign it is the same as fit, so it is h minus 2 dih, and an overall factor of minus alpha or plus alpha or whatever, that doesn't really matter. The conclusion is that this Maxwell equation is solved if h is a harmonic function. And the conclusion that you reach for the Einstein equations is that all of them are solved if h is a harmonic function in R3, because this is the Laplacian in R3, or better, because R3 is not does not tell you anything about the metric, three-dimensional Euclidean spacetime, which is R3 equipped with the Euclidean three-dimensional metric. Okay, and we know that this h then can be expanded in spherical harmonics, and depending on your preferences, well, now you can select solutions with certain symmetry, okay, or with certain properties. We are not going, typically you only take the monopole solution, so you will consider that this is a constant c, and it turns out that people have checked what happens with higher monopoles okay, which are the ones that do not have spherical symmetry, and they only lead to singular metrics. There is a whole paper by Hawking and Hartle in which they argue that the solutions that I'm going to write now are the only ones that actually give you regular solutions. And these are these Papa-Petro-Majumdar solutions. Okay, and those solutions are, well, a linear combination of terms of the form qi divided by x minus xi, with, if you want, n poles like this. Okay, so this gives you, replace this h in the metric and the electromagnetic field, and this gives you the Papa-Petro-Majumdar solutions. Well, what can we, how can we interpret these solutions? This is, every time you get a solution, there is a whole problem of the interpretation of the solution. If you want these solutions to be asymptotically flat, with the standard normalization, you immediately see that you have to take c equal to 1. So plus normalization. If you ignore this c equal 1, clearly when you only have one of these terms, so this capital N here is only 1 and there is only one pole, if you shift the origin to this to the corresponding x and you call this absolute value of x equal to rho, you get the Bertotti-Robinson solution. If c is equal to 1, it is not 0. Then 1 plus this, it is the extremal Reissner-Nordström solution. So when you have more poles, what do you have? What do this solution does this solution represent? Because clearly, when you are close to one of these poles, okay, so if you are you have many n's, but you get close to some x, that let me call it x star, then this determinant, this denominator blows up, the particular for I equal star, blows up or grows much bigger than the rest, and you can ignore the rest. So the metric is approximately equal to the metric of a single Reissner-Nordström black hole. So near each of these poles, the metric looks like a extremal Reissner-Nordström black hole that has a horizon at the point x equal to x star, because if you change coordinates, this will be rho, okay, and you know that the horizon was at rho. So the conclusion would be that this is a collection of extremal black holes which somehow are in equilibrium. Okay, now we are going to compute the masses and charges and so on and see how this can happen. Well, I have said too soon, maybe, that they are in equilibrium, because I haven't said anything about these signs. If the signs of these QIs are not all positive, okay, I have chosen c equal to 1. So once I choose this 1, then the rest have to be positive. Well, if some of them are negative, then there will be points in the space-time for which h vanishes and which do not coincide with the poles, which are the horizons. This metric only describes what is exterior to all these horizons, nothing inside of the horizons. And so if there are points where h vanishes, then immediately you see that there is a divergence here, and you can see that indeed there is a curvature singularity there. So you have to take, these solutions are only regular if all these QIs have the same sign. So QIs all positive for all I. And then, well, there is, maybe I will mention in the end what can be the interpretation of these singularities. So let's focus first on the case on which there are no singularities at all. If there are no singularities, then there is nothing that prevents us in principle from interpreting the solution as describing a set of extremal black holes which are somehow in equilibrium, and which is something that we will have to explain. We didn't search for solutions with two Schwarzschild black holes in equilibrium. But we didn't expect the theory to describe such a thing, because clearly there is no Newtonian limit for that. There cannot be two masses in static equilibrium. Okay, I should add the word static, because they could be in orbit one around the other, and still that is not equilibrium either, because we know that if a black hole orbitates around the other, then there will be an emission of gravitational waves, and the whole thing is not in equilibrium. Okay? So how do we justify that this is a set of black holes? Okay, well, we can compute the mass. Well, the fact that these are horizons can be, if we know how to extend the metric beyond rho equals 0 in the case of one black hole, since the metric can be approximated by just one black hole when you get to rho equal to 0 in these coordinates, or to x going to x star, then immediately you can extend the metric in the interior of that black hole. So there is no doubt that this can be done. Okay. But why is there such a thing? The interpretation is that, okay, if each of these black holes satisfies this relation that the mass is equal to Qi, which is true if there are no other black holes, then you may think that multiplying two of these equalities, okay, this should be J, and then you multiply, and somehow you find that divided by the distance, all the charges have the same sign, so they can be positive or negative. The overall sign of all the charges is in this alpha. So this corresponds to a situation in which the black holes are in equilibrium because they attract the same as they repel electromagnetically. The gravitational attraction is counter-arrested by the electrostatic, in this case, repulsion. You may wonder how is this possible, because well, there are no terms that of interaction in the Einstein-Maskwell Lagrangian. The only term is f squared, but there is no coupling. Nothing tells you how particles couple to the electromagnetic field and why there is repulsion between charges. This doesn't seem to be written or indicated in the Einstein-Maskwell Lagrangian. If you study quantum electrodynamics in quantum field theory, you will see that there is an interaction term between electrons and the electromagnetic field, and that tells you that two electrons will repel. That term is not present in this Lagrangian that we have considered. However, you should remember at this point that we were able to derive the Lorentz force term and the loss of motion of a particle with a single charge from the Einstein equations, and that is because the Einstein equations know everything about energy, interaction energy. Then observe that the energy momentum tensor of the electromagnetic field contains interactions. It is of order f squared, so it contains the energies of interaction. And from the energies of interaction, you can find what are the forces of interaction, the intensity of this interaction, even if it is not explicitly indicated. The Einstein equations know that because there is an energy of interaction between all these black holes that have certain charges, there is some force between them, and that force is precisely cancelled by the gravitational force. And this is how you get a static solution. Well, the point of talking about these solutions, okay, is precisely to make you notice how powerful the Einstein equations are, the fact that they don't need additional equations to tell you that two charges repel each other. Everything is contained in there because you only need to know about the energy. And the other lesson, apart from the fact that you have learned that there are other solutions, is that we will stress in these coming videos, is that when you have extremal black holes, the near horizon limit is of this ADS2 cross S2 form. Okay, this is a sort of universal law. When black holes are non-extremal, and the temperature, we will see that the temperature of black holes which are non-extremal is different from zero, then the near horizon limit is different. And you can learn about the temperature just by looking at this near horizon limit. There are many other properties that can be learned from this limit. Okay, and this is the end of this video.